So glad you stopped by. So anyway, as I was saying, Robert, Robbie, Bobby, Bob, let's go with that. Try to make these videos somewhat entertaining, for the students. Really do, while at the same time trying to get information in there they need in order to learn the math and be able to do the assignments.
Oh, that's really cool. I appreciate the kind of complexity of it.
So back when you were in high school, you were a big fan of math and math class, right?
Sure.
Yeah, that's cool, man. I was talking with our principal, Dr. Guthrie, this week. You did know that he graduated with his doctorate, right?
Yeah, he's becoming a better guy.
Yeah, we were talking about, we've got all these lessons out there, all these great lessons, and some students they're skipping the videos and just going straight to the assignments and trying to do the assignments without ever learning the lesson. I mean, that wasn't you in school, right? You were one of the ones that paid attention to the lesson, right?
Sure.
Yeah, some of the students, they're really sharp in math, and they don't have a lot of problem doing that. If there's something they don't understand, they look it up on the internet, and they seem to do okay. But there's a lot of these students that, man, they have no idea what's going on. You can tell by what they make no sense with the answers they put on there. They really need to be watching the video.
Are we promoting a movie?
Oh, sorry. Where was I?
Your foot's starting to jump a little bit. You better get to your next question.
Right. So we're just about to wrap up the school year, and
What are we doing?
oh man, it's late. I got to do a lesson. I got students waiting on me. I'm sorry. I got to run.
Bye.
Oh, cue my intro. We don't have long before all you seniors are going to be looking to run away forever. So we got to get the rest of our curriculum done so you guys can be free and run off into the wilderness or wherever you're running off into. So not all of you are seniors, but the vast majority of this class is seniors. So there's a lot of you folks that are looking to get out of here. So let's see what we can do to help you get along. All right, let's pull up our lesson for this week. Our lessons, we have 2 lessons this week. All right, going to our grade screen as usual to see where we're at. We scroll all the way down and we are done with matrices. No more matrices. Hopefully you've got all that turned in, and most of you do. There may be just a few folks that haven't finished a couple of the last assignments, but this class is doing really well at keeping up and not getting weeks and weeks behind. Nobody in here is more than a week behind tops. So congratulations to you, class, because that is unusual. Usually I have somebody that's 2 or 3 or 4 weeks behind, and this class has nobody that is 2 weeks behind. A few of you are 1 week behind, but that's easy to catch up. All right, looking at this, we have 2 lessons this week, 2 lessons next week, and 2 lessons the last senior week. Quadratic functions, polynomial functions of a higher degree. That's what we're going to look at. Now, the quadratic functions, a lot of that's like we've been doing quadratic functions for years. Yes, we won't spend as much time on that lesson as we will the second one, but we're going to look at quadratic functions in just a little bit different way this week. So let's look at 801 and 802. So close conics, close the matrix folder. Nice. All we have left is this Module 8 folder down here. Quadratic functions lesson right here. And we're going to be taking a lot of notes because we got to keep all this straight, especially our second lesson. All right, we're back to these lessons that give us a scenic overlook at the top. And so we just go through the scenic overlook until we get to this colored section down here. And there's red and blue and all of that. When we get to that, that's the lesson. This is the overview of the lesson, and then this goes into more detail, gives you more examples, just spends more time in each of the topics. So that's for you to read if you need more help after we go through the overview, that there's lots more information for you throughout the rest of the page. But we're going to cover the highlights up here and just hit what this lesson is teaching us. So in the next two sections, we're going to look at polynomial functions today. That's today. And we're going to start out with just focusing on quadratic functions. But let's define what a polynomial function is. And this is real mathy. This is like college level mathy terms that I'm going to throw at you. And then we'll make sure that we understand what it means. So let n be a non-negative integer. Well, non-negative just means it's a positive number. And an integer means it's not a decimal. So n is a non-negative integer. And let a sub n a sub 1, a sub 0 be real numbers where a sub n can't equal 0. So it's just saying it's a number. It's a term number. So f of x equals a sub n and then x raised to the n power. So that's just saying a sub n can't be 0. So that means there's a coefficient, even if it's 1, maybe it's 1, and you have x raised to whatever that power is as well. And then you'll have another possible term, a sub n minus 1, x n minus 1, all the way down to just a sub 0. So it's basically saying a polynomial function has an x in it somewhere. And it may have an x squared, or it may have x to the 5th. It may have an x to the 11th power. It's just an equation, or an equation here that has a variable. That's a polynomial function. That's a fancy math way of saying that, talking about all the a sub n not equal to 0, etc. So this would be a polynomial function with x with degree n, because it's x to the n power. All right, so don't let this definition scare you. Each a is called the coefficient, right? We're saying it has a coefficient. The coefficient's not 0, or else that term doesn't exist. And we write it generally in descending order. We write x to the 3rd, and x to the 2nd, and x, and then the constant. That's the standard way of writing it. The highest degree goes at the beginning. And we classify polynomial functions by degree, right? If it's x to the 4th, that's a 4th degree polynomial. If it's x squared, that's a 2nd degree polynomial, which we also call a quadratic. So let's look at quadratics. Definition of a quadratic function. Let a, b, and c be real numbers with a cannot be 0. Notice that means b and c can be 0, but a cannot. So the function of x is given by f of x equals ax squared plus bx plus c. So that just means the x squared term has to exist for it to be a quadratic function. We don't have to have an x or a constant. It can just be f of x equals 1x squared. That's all we need. The rest of these can be 0 to be a quadratic function, but we have to have the x squared or it's not a quadratic function. And we know that the graph is a U-shaped curve called a parabola. We know the parabolas are symmetric around a line called the axis of symmetry, right? That's the line that goes right through the middle of the parabola. It looks like a mirror image on the left and the right. It goes through the axis of symmetry, or we just call it axis, the axis of the parabola. And it goes right through the vertex. The axis of symmetry intersects the parabola called the vertex, and that's the point where the parabola turns and goes the other direction, right? That's the lowest point or highest point with an up and down parabola, the vertex. And we know that the parabola opens upward if the leading coefficient's positive. If that a in the x squared, if it's 2x squared, it's going to be going positive. But if it's negative 2x squared, we know that the parabola opens downward, right? So the simplest quadratic function is just f of x equals ax squared. And it could be a equals 1. Maybe it's just x squared. And in this case, we know we have a vertex of 0, 0 because there's no movement off of the origin. And we know that the axis is the y-axis. That's the axis of symmetry is the y-axis. And we know it opens upwards if that a is a positive number and down if that a is a negative number. All right. Let's talk a little bit, just very briefly, on what the graph would look like of different quadratic equations. We know what x squared looks like. We're going to pull up Desmos just to play with and refresh our mind here, that if we have y equals x squared, we know what that looks like. That's a normal parabola. We're used to seeing that. But what about if it's 1/4 x squared? See, the a there is 1/4 x squared. So what happens if there's a 1/4 in front of that? 1/4 x squared. Look there, it looks very similar to the original parabola, except it's wider. It still has the same vertex. It still opens upward. It goes on forever. The only difference is if it's 1/4, it's wider because it's only going up 1/4 as fast. Notice when the parabola gets up here, when x is 2, the function equals 4. But in this one, since it's only 1/4 as fast, when x equals 2, it's only at 1 instead of 4. Where's that? There it is, 2/1. 2/1 compared to 2/4 up here. So it's only 1/4 the value of the original parabola. What if it's 4 instead of 1/4? Well, let's change that. Since this made it go up 1/4 as fast, the 4s are going to make it go up 4 times faster. So by the time the original parabola has only made it to 1, when x is 1, it's at 1. But for the new parabola here, it's 1/4. It's going up 4 times as fast. So that's what that coefficient out front is doing to our parabola. Now, if we have a 4x squared plus 4, exact same parabola, it's just that the vertex and the entire graph has shifted upward 4 spaces. So we're not at 0, 0 anymore. We're at 0, 4 because it's gone up 4 spaces. And let's see, negative 4x squared, we take away the plus 4 and just put a negative. We know that just means it opens downward. Exact same shape, still 4 times as fast as a regular parabola. It's just going downward. And 4x or x squared minus 4, we know what that one does. Because we did plus 4 and it went up. If we do minus 4, it goes down. Down. And the last one it has is 1/4 x squared plus 4. Let's put that 1/4 back out front. And it's just a much wider one, and it's shifted down 4 at the same time. So just refreshers on the transformations that happen with a quadratic form. Here's the meat of what we're going to look at today is the vertex form of a quadratic function. So the vertex form, so we're going to take notes today. So we're going to write the vertex form in our notes. F of x equals, and how they got that? A times x minus h squared plus k. All right, so if I put that in my notes, just to start out my notes for the day, the vertex form of a quadratic, make sure we know what we're doing the vertex form of, is a times x minus h, in parentheses, squared, plus k. And the vertex, that turning point, is found at hk. Whatever the h is in the parentheses, that's being subtracted, and then the k. So to convert an equation, and that's an important thing to look at, we have to use what's called completing the square. And I'm sure you haven't done that a whole lot, so we're going to run through an example of that just to refresh our memories on how we complete the square. And I'm going to use this example right down here. So here's somewhere you can walk through and see, do I know what I'm doing? And you can check your answers when you're done. If you click on that, it's got a little box that opens up and it'll take you to a Google Doc that I have saved with the answers for A and B. We're going to do A together. See, there's A and there's B. All right, so this wants to know, put this into standard quadratic, put the following into standard quadratic function form. Well, it's in standard form. find the vertex point and the axis. We're going to put it in vertex form. So we're going to walk through how to do that, completing the square. So let's write this function down. It's 3x squared plus 12x plus 7. And they do have an example right there you can follow through to see how this works. But I want to work this on our notes and go through an example. So we have it already in standard form, right? This is the standard form. This is the vertex form. I think I'm going to highlight the vertex form because that's kind of what we're working with today. If we have it in standard form, where we have 3x squared plus 12x plus 7, we want to get it in vertex form so we can identify the vertex and the axis of symmetry. So we do this by completing the square. So we're going to kind of group the terms that have the x's in it, and we're going to factor out just the coefficient. So we're going to say f of x equals 3, and I just want an x squared equation. And then we got the plus 7. So I've just factored out the 3. So I have x squared plus 4x because it's a lot easier to work with just an x squared when we're dealing with trying to solve quadratic equations. And I want to make this a perfect square trinomial. And you're like, what is a perfect square trinomial? Well, let me refresh your memory. If we have, let's say, x minus 3 squared. So we're taking a binomial and squaring it. If we square a binomial, we'll end up with a perfect square trinomial. So that's the same thing as x minus 3 times x minus 3, right? We're squaring that trinomial. And we do that by distributing. So that equals x times x is x squared. X times negative 3 is negative 3x. Now let's distribute this. The negative 3 times x, and then negative 3 times negative 3. So x minus 3 squared is x squared minus 6x plus 9. This is a perfect square trinomial. So we know if we see this trinomial, we know it factors to this, because this is a perfect square, and it's the square of x minus 3. So we're trying to create the same situation here. Because if I can figure out a binomial that's a perfect square of, I can convert it to this, x minus h squared, x minus 3 squared. So I'm going to create that situation. And so there's a way we can do that. We take that middle term, that 4. So we're going to take that 4, and we're going to divide it by 2. And 4 divided by 2 is 2. And then we're going to square it. So 2 squared is 4. So what we're going to do is we're going to say, okay, so this equals x squared plus 4x. And if I had a plus 4 on the end of it, then this would be a perfect square trinomial, because I made it a perfect square by taking this, cutting it in half, and squaring it. But that changes my equation if I add 4 in there, right? It didn't have the plus 4. So I've also got to subtract 4 because I don't want to change the equation. So if I add 4 and subtract 4, nothing's changed. And I did that inside the parentheses, which means everything inside here is being multiplied by 3. So let me continue rewriting this. So there's 3 times x squared plus 4x plus 4. And I'm going to move this outside the parentheses. But it's not just the 4 being moved outside. It's plus 3 times negative 4. Right? Because 3 is being multiplied by x squared. 3 is being multiplied by 4x. 3 is being multiplied by 4. 3 is being multiplied by negative 4. So I'm still multiplying 3 by everything. It's just I broke this one out separately just to write it by itself. So this is still the same equation that I had up here. I just added a 4 and subtracted a 4 inside the parentheses. And now I'm breaking it outside the parentheses. So now this, oh, we're getting somewhere. This is x plus 2 squared. I know it's a 2 because that's the number I got when I cut this in half. X plus 2 times x plus 2 equals x squared plus 4x plus 4. 3 times negative 4 is negative 12 plus 7. So this all could be rewritten as 3x plus 2 squared minus 5. This is the vertex form. Notice it looks like that. So our vertex, this is x plus 2, but it's x minus h. So what is h? Well, this must be x minus negative 2. That's the only way we could have x plus 2 is if we subtracted a negative number. So our vertex is at negative 2 because that's what the h is. And the k, our k is a negative 5. And our axis of symmetry is x equals negative 2 because that's what our vertex is. So there's the vertex and the axis of symmetry for 3x squared plus 12x plus 7. We just had to rewrite it in vertex form and then pull out the vertex. And we'll double check ourselves. How will we double? Let's go to Desmos. That's the easiest way to double check. If you're trying to find a vertex and everything, and you want to know if you're right, go here and graph it. 3x squared plus 12x plus 7. There's the original equation, which does have a vertex at negative 2, negative 5, which is what we calculated. And to know if we did it correctly in vertex form, let's enter the vertex form and see if it's the same graph. Y equals 3 times x plus 2 squared minus 5. Oh, look, the green graph and the red graph are exactly the same graph. So we must have done it correctly because we said it was the same quadratic function, just rewritten in vertex form. So if the graph is identical, it is the same function. So that's how we double checked our work right there. And if we look at the check your answers form here again that we had just a moment ago, we'll see the first problem here, problem A. Vertex, negative 2, negative 5, and the axis is x equals negative 2. All right, so we checked your answers correct. So there's another one that you can try right there, and it's simpler because it's just an x squared. You don't have to factor out that 3 that we did. You can just take those first 2 terms and try to make it a perfect square trinomial. And then it says graph these to show that and check your graph, which is what we did. All right, to solve a quadratic equation, set equal to 0. Right, that's how we do it. We set it equal to 0, and if it's factorable, we'll factor it. And then we'll set each of the factors equal to 0. But if it's not factorable, or if it's nasty factorable, it's like we don't want to even try to do that, we can always use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac over 2a. Right, where a, b, and c are from the standard form. The a, b, and c are found right there. And you can use the quadratic formula. I'm not going to go through. Here's an example where they give you this. I'm not going to go through one of these because I know you've done the quadratic formula a lot in previous algebra classes, and we need to move on to our next lesson. That's the end of this lesson right here. But it's really about finding the vertex and the axis of symmetry and solving it some if you solve it and by factoring it. All right. Oh, let's talk real quick while I'm at these notes. Like this equation, if we wanted to solve it and set it equal to 0, this is one that factors. 0 equals factors is x minus 3, x minus 3. You know, because we know it is because we created this by multiplying those together. So what is the solution here? 0 equals, oh, I don't have to put the parentheses if I'm going to separate it. 0 equals x minus 3 is one of the solutions, and the other solution is 0 equals x minus 3. So if I add 3, x equals 3. If I add 3 over here. So what's the solutions? The solution is x equals 3 And we can say it has a duplicity of 2. Duplicity just means there's a duplicate. There's 2 of them the same. If we say it's a duplicity of 2, there's 2 answers the same. There is. They're both x equals 3. So if we graph that, we're only going to see it touch the x-axis one time. In fact, let's do that. X squared minus 6x plus 9. X squared plus 6x plus 9. Look at that. It only shows one solution, negative 3. Oh, negative 3? Oh, it's minus 6x. Minus 6x. I put the wrong sign. There it is. It only shows one solution. It only touches the x-axis one time. But there are 2 solutions because it's a quadratic equation. Remember, quadratic equations have 2 solutions. But sometimes they're imaginary, or sometimes it's the same solution twice. In this case, it's the solution x equals 3 with a duplicity of 2. So anytime you have this as a factor, if we have an equation that looks like this, equals, and we could leave it in factored form. This is not a quadratic equation. This is a higher one because it's a x squared and an x to the third. But still, we know the solutions to this. 3 and negative 1. And there's actually 2 3s and there's 3 negative 1s. There's 5 solutions to this equation. But these repeat. There's 3 of those. And these repeat. There's 2 of those. 2 3s, 3 negative 1s. So pointing that out because you're going to have a question like that in our assignment. Let's look at the assignment for the quadratic functions lesson. Find the vertex. And this is in vertex form. Oh, they made it real easy on you. They put it in vertex form. What's x? What's h? Find the vertex of this. This is not in vertex form. Find the axis of symmetry. Well, if you can find what the vertex is, right there, whatever the x is, x equals 3 is the axis of symmetry. And if you graph that and know what it looks like, it's that purple line right there that goes right through the vertex. That's the axis of symmetry. Write this quadratic equation in vertex form. So if you complete the square, like I did in that sample problem, which one of these equations you end up with? And here's when it says a projectile is thrown upward. So the distance above ground after t seconds is given by the function h of t equals negative 16 t squared plus 640 t. Now that's a quadratic equation. They're just using t instead of x. Just using t instead of x. So this is a quadratic equation. And notice it's a negative. So it's a parabola that opens downward. So it does have a maximum height. This projectile is thrown upwards. After how many seconds does the projectile take to reach its maximum height? Show your work for full credit. So what is the maximum height? That would be the vertex of the parabola, right? If the parabola is going downward, it has a maximum vertex. So after how many seconds? It says seconds was the t or the x. From the vertex, it'd be the x value of the vertex. That's how many seconds. So make sure you answer the question after how many seconds, which means you want the t value or the x value if you're thinking in xy terms. So there you go. That's the 5 problems for the quadratic functions lesson. Now let's move on to polynomial functions of a higher degree. This will take a little longer than the quadratics did. Okay, here's our scenic overlook. Graphs of polynomials. So in previous lessons, we learned to identify graphs with a degree of 0, which would be like y equals 3, right? It's just a horizontal line at 3. Degree of 1, that's just a linear equation. Y equals x plus 1. Y equals negative x minus 5. And 2, that's quadratics, x squared. And we know how to draw all of those, linear and just horizontal lines and parabolas. But graphs of polynomial functions greater than 2 are not so easy to graph because they could be all kinds of crazy wild shapes, right? It's easy for degree 2 or less because it's always a parabola for a quadratic. It's always a line for linear. And if it's a degree of 0, it's always a horizontal line. So let's look at some of the basic features of the polynomials that have degrees greater than 2. General features. So this would be of all polynomial graphs. They are continuous. That means if you graph them, there's not going to be gaps. There's not going to be holes in the graph. Like we had holes in the graph when you have rational functions, but you don't have that with polynomial functions. So they're continuous. It's some long curve, right? It may go up and down, or way up and to infinity, negative infinity. And there are no sharp or pointed turns on the graph. There's no sharp or pointed. The graph is smooth and rounded. So polynomials with the easiest to see are called monomials, where it's just x to the n, where n is an integer greater than 0. And the bigger it is, the greater it is. Here's the thing. If the largest exponent is an even integer, then it's going to be U-shaped like a parabola, even if it's a bigger number. And if it's odd, it's going to shape like an S somewhat, if it's just one term. So let's look at what it's talking about there. So it says if it's just one term like that, and it's even. So let's change this from second degree to like 8th degree. X to the 8th. Look, it's U-shaped. It's U-shaped, and it's not pointed. It says it's always curved. See, it's curved. Feels very flat. If we made it 28th degree, that's still an even number. It just gets flatter. But still, it's going to be curved. It's not going to have jagged edges. It's not going to have points. Even if we make it 128 degrees. Like x to the 128th degree. It's not a point. It's still a curve. It's still curved. And if it's odd, it says it's an S. So let's change it to like 5th degree. I did it backwards. 5. There we go. So it's like an S, kind of. It goes over and up. And if it's the 15th, that's still odd. It just gets a little flatter in the middle. 125th. It looks like it's pointed, but if we zoom in, we can see it's still curved. See, it's not going to have a pointed sharp edge even at 125 degrees. But you see, it's an S-type shape for an odd function. So that gives us a little expectation in our head. If it's even or odd, it kind of gives us an idea of what the basic shape should look like. So x to the 3rd, that should be like an S. Negative x to the 3rd. Oh, yeah, what happens if it's negative? Let's just make this the 3rd again. So there's the 3rd. If it's a negative, it's still an S. It just flips over. Where now the negative goes up to infinity and the positive side goes to negative infinity. Where when it was positive, we went to negative infinity on the negative x's, and the positive x's went to positive infinity. So the negative just flips it upside down. All right, just flips it upside down. But still, it's an S shape. It's just upside down. X to the 4th, that's going to be like a U, like a parabola, except a little flatter. X to the 4th plus 1. It's going to be a U. It's just going to be translated up 1, shifted up 1. X plus 1 in parentheses to the 4th power. Wait a minute. If we put it in parentheses, we'll put X in parentheses here. And we're going to put a plus 1 inside there with it. It just shifted it left 1. If you remember translations, anything with the X is going to shift it left or right. If we put minus 1, it's going to go to the right. If we put minus 3, it's going to go, I changed the wrong thing. It's going to go 3 to the right. So that's what it does when we change inside with the X. And 1 minus X to the 4th. Oh, that's a good one. What happens when we do 1 minus? 1 minus makes that a negative X to the 4th. Flips it upside down. And the 1, this is the exact same graph as saying y equals negative X to the 4th plus 1. It's the same graph. It's just you're rearranging the terms and putting the 1 first. But it's the same as negative X to the 4th plus 1. Same graph. All right. Here's the big thing we're going to talk about today. the binomial theorem and Pascal's triangle. Expanding a binomial, which is what we did with that quadratic. We took x minus 3 squared and we expanded it to x minus 3 times x minus 3. But we can do that with larger exponents. You know, a plus b to the 0 power is just going to equal 1, right? Because anything to the 0 power equals 1. A plus, man, let's put this in our notes. Well, in fact, let's write this out and talk about it as we're looking at it. So if we're going to expand some binomials, and we start with just a plus b to the 0 power, well, that's just going to equal 1. Because anything, focus, there you go. Anything to the power of 0 equals 1. Anything. And if we do a plus b to the first power, that's just going to equal a plus b, right? Because anything to the first power is just itself. All right. Hopefully our focus is going to get better here. A plus b to the second power. That's going to be a squared plus ab plus b squared. You know, and that's a quadratic, because like we saw, x minus 3 gave us a quadratic equation where you got the x squared. You have a plus b to the third power. Starts out with a to the third power. And then, let's see, then you have, oh, this was 2ab. That's why I was wrong with that. I'm like, wait a minute, it's not just ab, it's 2ab's. Something looked wrong there. And this is 3a squared b plus 3ab squared plus b to the third. There's a pattern that evolves here. If we had a plus b to the fourth power, we'd have a to the fourth power plus 4a to the third power b plus 6a to the second power b to the second power plus 4ab to the third power plus b to the fourth power. You're like, my goodness. And we could keep going. But I want you to notice that there's a pattern that evolves. When we have the third power, look what happens to the a's. The first term has a to the third power. The second term has a squared. The third term has a to the first. And this one, the a is gone because it's a to the 0 power. A to the 0 power is just 1. Meanwhile, what's happening with the b's when we have to the third power? There's no b here. It's b to the 0 power. Then it's b to the first power. Then it's b squared. Then it's b to the third power. You see the pattern? A plus b to the fourth power. There's no b. B to the first, b to the second, b to the third, b to the fourth. What about the a's? A to the fourth, a to the third, a to the second, a to the first, no a. Notice that pattern? So that's what's happening as we expand higher and higher exponents of these binomials, expanding binomials. Now, what about, you're like, okay, Mr. Brock, I get that, but where are you getting this? You've got numbers, coefficients in there. And you didn't get that from doing this. No, I didn't. We're going to look at two ways to get those numbers. One is the binomial theorem, and the other is Pascal's triangle. Now, the binomial theorem, we're going to look at this just because I don't think you've looked at this ever in your high school career, and I don't want you to get out of high school without seeing it at least once. I want you to look at this here. This NCR equals N exclamation point divided by R exclamation point divided by N minus R exclamation point. And you're like, okay, are you saying that's math? It is math. So it talked about x minus 3 to the fourth. So we're gonna look at that a little bit more ourselves. And it says that you can find NCR for R equals 0, 1, 2, 3, and 4. Let me write down this formula that they put there just so we can see what in the world are they talking about with these exclamation marks in my math here. You may have seen some memes on the internet. It'll say, would you believe that 1 times 2 times 3 times 4 times 5 equals 5? And you see these memes and people arguing the math. What in the world? 1 times 2 times 3 times 4 times 5 equals 5. Well, in math, this is called factorial. 5 factorial. These are factorials. And the definition of 5 factorial is you multiply every number up to 5 times each other. This is what 5 factorial actually is. 1 times 2 times 3 times 4 times 5. If I took 3 factorial, that is 1 times 2, 2 times 3. 3 factorial equals 6 because it's 1 times 2 times 3. 5 factorial, 1 times 2 times 3, which is 6 times 4 is 24. So it actually equals 120. Because 1 times 2 times 3 times 4 times 5 is 120. That's what this is. When you see an exclamation mark in a math equation, it's talking about the factorial. You have that button on calculators. You may have seen it and go, I don't understand why I have this button on a calculator. Let's see if our plain little calculator has it somewhere. Let's go to second and see if it. Okay, it doesn't have it on my plain basic calculator. What about, does my trig one have it? Function have it? Okay, this little plain calculator. Oh, there it is. I'm missing it. It's right there. In factorial. So if I put in a number 5 and hit that factorial button, it's 120 because it's 1 times 2 times 3 times 4 times 5. It has the factorial button right there in your calculator. If I want to know what 8 is, that's a lot bigger number. 8 factorial is 40,320 because it's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. But that's what that factorial button is. And it's used in higher math. So this is saying that we can find the coefficients by using this for x minus 3 equals to the fourth power. So what it's saying is n is 4 because that's the fourth power. And the r, we try to find the first term, the 0 term, the first term, the second term, third term, and fourth term. So it says if we calculate this, we can take 4c0 to find the coefficient of the first term. So that would be the n is the first number, 4 factorial divided by 0 factorial. What is 0 factorial? Let's put it in our calculator. 0 factorial is 1. Interestingly enough. I don't know how that works. 0 factorial is 1. So this is just equal to 1 times 4 minus 0 factorial. So this simplifies to 4 factorial over 4 factorial, since that's just 1, which equals 1. So that's the coefficient of the first term. 1 x to the fourth. Right? Because we know the a is to the fourth power and the b doesn't exist in the first term. For the second one, 4c1, because we're going to take the r and we're going to go from 0 to 4. 4 factorial over 1 factorial minus 4 minus 1 factorial, using this formula, 4 minus 1. Well, 4 factorial over 1 factorial, that's the same as 0 factorial. Let's look at this. 1 factorial. That's the same as 0 factorial. It just equals 1. So it's 1 times 3 factorial. So if you had 1 times 2 times 3 times 4. I don't write 3's very well, do I? Over 1 times 2 times 3. These cancel out. It just equals 4. So our second term has a coefficient of 4. And then we take our pattern, x to the third, and then it's multiplied by -3 because we do have a b to the first power. B is -3 in this case. We're going to run out of room here. I'll have to write it up here, and then we'll summarize it there. So, all right. To find the next term, 4c2 be 4 factorial. It's always 4 factorial on top because it's whatever the n is, over 2 factorial, 4 minus 2 factorial. So that's 2 factorial times 2 factorial, right? So it's 4 factorial on top, 2 factorial times 2 factorial. All right, so if we want to use our calculator, what is 4 factorial? It's 1 times 2 times 3 times 4. That's 24. 2 factorial is just 1 times 2, right? 2 factorial. So this is just 2 times 2, which is 4. So 24 divided by 4 is 6. So the next one has a coefficient of 6, which we saw up here. A squared, x squared, and the b squared, -3 squared. There's the next term. All right, let's get our next term. 4c1 equals 4 factorial. Oh, I'm sorry, 3. We already did 1. We're going up. C3. 3 factorial and 4 minus 3 factorial, which is just 1 factorial. So that goes away. So this is just 4 factorial divided by 3 factorial, which we did that one up here. The 1, 2, 3 cancel out. So this just equals 4. And we have one of the a's, which is x, and we have -3 to the third power. And then the last term, we can figure the 4c4, 4 factorial, 4 factorial, 4 minus 4 factorial, which is just 0 factorial, which is 1. 4 factorial divided by 4 factorial is just 1. So we know this is just -3 to the fourth power. So using the binomial theorem, we can figure out what those coefficients are. 1, 4, 6, 4, and 1. Then we just simplify this. So this equals x to the fourth plus 4 times -3. So this is a -12. X to the third plus 6 times -3 squared. -3 squared is 9. So 6 times 9 is plus 54x squared. Then this last one over here, -3 times -3 is to the third power. I'm sorry, -3 to the third power is -27 times 4. So that's -108x. And then -3 to the fourth power. -3 times -3 is 9. Times -3 is -27. Times -3 again is 81. So this is what this equals. And we did it with the binomial theorem, figuring out each coefficient. The other way we could do this is we could take x minus 3 times x minus 3 times x minus 3 times x minus 3. 4 times. We'd have to distribute that and multiply these together. And then take the answer there and multiply it times another x minus 3 and distribute all that. And then take that answer and multiply it by another x3. And we should end up with that right there. Let's see. Is this one of the samples they did? They did x minus 4 to the fifth. So I can't check our answer, but that is how it works. X minus 3. Now, that being said, and you're like, wow, that's a lot of work, Mr. Brock. Well, you can do it either way, right? If I gave you a problem like this, you could multiply it all. That's a lot of work too. There's not an easy way to take binomials and do it 4 times. However, Pascal's triangle gives you another way to get these coefficients. That is a lot easier than this. And you're like, oh, thank goodness, Mr. Brown. With the binomial theorem, it's easy to understand this. I mean, you got to look at it a few times, but you kind of figure out if it's a third power, then I do third, second, first, 0 for the A term, and for the B, I go 0, 1, 2, 3. We can figure that pattern out if we look at it enough, right? That's okay. But the coefficients look a little bit wacky. Well, there's something called Pascal's triangle. Pascal figured this out. He was a pretty smart guy. Pascal. He figured out that if you have a something or other to the 0 power, it just equals 1. Right? And if you have two things, a binomial, a plus b to the first power, you're just going to have a coefficient of 1 on each one. Which, right, it's 1a plus 1b. Right? And then he figured out if we have it whatever to the second power, it's a 1, 2, and a 1, which we saw that. A squared plus 2ab plus b. And then it's a 1, 3, 3, 1, and it's a 1, 4, 6, 4, 1, and it's a 1, 5, 10, 10, 5, 1. This is Pascal's triangle. I'm illustrating it. How did I get this? Oh, Pascal's pretty smart. He figured out if you add these two together, you'll get the middle term. If you add these two together, you get that term. If you add these two together, you get that term. You just keep adding together the numbers above it. So if I want the next row after this, which would be to say this is third, fourth, fifth, sixth power. So if I have a plus b to the sixth power, the ones stay on the outside. And then you add those two together. So there'd be a 6. And then you add those two together, and that'd be a 15. Add those two together, and that's a 20. Add those two together, it's a 15. Add those two together, it's a 6. And put a 1 on the outside. Look here, for the fourth power, we found out the coefficients were 1, 4, 6, 4, 1. Down here, Pascal says, oh, the fourth power is 1, 4, 6, 4, 1. Just by adding the ones above it. So you may like Pascal's triangle better than the factorial method that the binomial theorem gives us. The binomial theorem uses this factorial method. Pascal says, well, if you just want to do all the triangle, you can use this to get the coefficients. Now notice that's not the final coefficient because you have a number here. -3 squared, -3 to the third. So you got to multiply those together. But this gives you the base numbers for the fourth degree, or the fifth degree, or the sixth degree, or the seventh degree, if you want to go farther. Pascal's triangle. And we do have that in the notes in the lesson. If you want to click right here where it talks about the binomial theorem and Pascal's triangle, notice if you click on that and go back to this sheet to where we got the binomial theorem, it also has Pascal's triangle down below. Let it load here. I'll show you. It starts it right there. 1, 1, 1, 1, 2, 1, 1, 3. If I go down here, it shows how it gets it. You take those and add it together to get the next row. 1, 4, 6, 4, 1. And you can continue it on. And it gives you the fifth row. Oh, that's the 1, 4, 6, 4, 1. And you can continue to expand that. So that is the binomial theorem and Pascal's triangle together. Let's see, leading coefficient. We'll talk about just one or two other things in here. Leading coefficients. Using the degree and the leading coefficient, determine the direction left and side. We've hit on this in the past. We're going to hit on it again real quick because it does ask you some questions on that. We're going to make this a little note chart. We can tell what the graph looks like of a polynomial function based on the degree, whether the degree of the function is even or it's odd, right? And then is the leading coefficient positive or negative? Even or odd? If it's an even degree, we know it's like a parabola, right? Squared, or it could be a fourth power, a sixth power. It makes a U, but the left end is going to go up and the right end is going to go up if it's positive. If it's a 2x squared, both sides got to go up. If it's a x to the sixth, it's going to go up. If it's a 10x to the eighth, it's going to go up. If it's a negative, we know both ends are going to go down. Negative 2x squared is going to be a parabola pointing down on both sides. However, if it's an odd degree, it's a third power or a fifth power or a seventh power or even a first power. X to the first is odd. The right side's going to go up and the left side's going to go down if it's positive. Now, in between, it may do all kinds of crazy stuff, just depending on what the equation looks like. But we're just talking about the end behaviors. End behavior. And if it's negative, it's going to be exactly the opposite. The left side's going to go up and the right side's going to go down. So this is our little cheat sheet to use. Based on the degree, whether it's even or odd, plus or minus, that's what the graph's going to look like. On the ends. In the middle, we don't know. This could be a W shape. This could be just a U. It could be all kinds of stuff. But we know what's going to happen on the ends. So it says using the degree and leading coefficient method, x to the fifth. That's going to be pointing up on the right and down on the left because it's odd and positive. The x to the fifth is. Look at this, x to the fifth. Plus 5x. Oh, I didn't put plus. No, where was it? X to the fifth plus 5x plus 2. There it is. Up on the right, bottom on the left. And this is just a very smooth curve. X to the fifth plus 5x. If I do a minus, it makes it do crazy stuff in the middle. But still, it goes up on the right and down on the left because it's a positive x to the fifth. Positive odd exponent. So you should be able to look at these. Here's a negative x to the fifth. It's a negative, it just changes, right? It goes up on the left and down on the right. And we'll make it a positive. It does that squiggly thing in the middle. So you can look at any one of these and tell what it's going to look like before you graph it. At least the ends. It may do weird stuff in the middle. So you can check yourself. You can look at that and say, do I know? And then you click on this and it'll pop up and it'll tell you the answers for all 6 of those. I don't remember if it shows graphs or just tells you. Let's look at this. Oh, there you go. Down, left, up, right. So it tells you what it should do. And zeros. Let's see what else we have. The intermediate value theorem. Yes, the intermediate value theorem. Zeros. So we know that. Let's see. I want to pull out a graph. Piece of graph paper here. Yeah, there we go. Let's have some graph paper. So if we have an equation that is f of x equals 2x to the fourth minus 3x third plus x plus 1. And I don't know what that graph looks like. It's going to be kind of an odd graph, right? But I do know a lot of stuff already. I know it's going to be even, so it's going to be pointing up on both sides because this is positive. And I know it can have 4 solutions. 4 solutions. Which means 4 zeros, which means it crosses the x-axis 4 times. Now I should say max. It cannot have more than 4 solutions. It cannot have more than 4 times that it crosses the x-axis, but it can cross the x-axis less. Let me do this. It will have 4 solutions. It's just some of those may be imaginary, which means it may be like 2i, right? Could have an I, that imaginary number in there. But it will have 4 solutions. Some may be imaginary. It may cross the axis 4 times. It may cross less, because if there's imaginary solutions, those will not show up on the graph, right? It may be twice. And if there's duplicate solutions, let's say the solutions are 2i, negative 2i, 4, and 4. This is a duplicate solution, which means when it gets to the graph there, it's going to bounce. It's not going to cross. It's just going to touch. So we can say touch. May cross or touch the axis. Touch x-axis. It's going to bounce. It's going to hit it and bounce right off of it. It's not going to cross it. It's just going to touch it. If it has the same solution twice, and these won't show up at all. So if we graph this, it's going to do something like this. You know, it may do something like that. We know it's going to touch at the 4, x equals 4, and it's not going to touch it anywhere else if these are the solutions. Now, it's probably not the solutions. I just wrote this down as an example. It probably is not that equation. In fact, I can guarantee you it's not that equation. So it's important to understand, looking at that, how many solutions we expect. There are 4 solutions. Now, here's something else that our lesson goes into. So it talks about the zeros. That's at most real zeros or solutions, or where the graph touches, and at most n minus 1 relative extrema. So it means at most n minus 1, which would be 3 extrema. What's an extrema? Extrema is max or mins, right? Maximum values or minimum values. So this one, let me draw this out just a little bit. We're a little bit neater. If the graph looked like this, it's a 4th degree. This is a minimum. This is a minimum. That's a maximum. Looking at this part of the graph, that's a maximum. Looking at this part of the graph, that's a minimum. Looking at this part of the graph, that's a minimum. And it's also the minimum for the whole graph. But there could not be more than 3 total n minus 1. It can't turn more than that. It can't have another dip down because it's only a 4th degree function. Since it's 4th degree, this is the maximum it can have. Is 3 maxes and mins. Can't do another loop as a 4th degree. And we know that just by looking at the equation. There's no way I can make it be more of a roller coaster than that because it's 4th degree. So that's emphasized in our lesson, that you can only have n minus 1 extrema. And know that these are all equivalent statements. And I know you know this, but let's review this. If we have a 0, x equals a is the 0 of the function, like x equals 4 on the one we just looked at. That's a 0 of the function. That's where it touches the x-axis. X equals 4. And x equals 4 would be a solution for the equation. If we set the equation equal to 0, x equals 4 is one of the solutions. That's the same thing as a 0. And a comma 0, like 4 comma 0, would be an x-intercept, which we saw on the graph. It intercepts the x-axis at 4 comma 0. So x equals 4 is a 0 because 4 comma 0 is an x-intercept, and it's a solution. And x minus 4 would be one of the factors. When we factor that equation, we'll get x minus 4, and we've set it equal to 0, we get x equals 4 as a solution. So x minus 4 is that factor. All right, the other thing I want to talk about is the intermediate value and the extreme value theorem, and that'll be the end of this. Intermediate value theorem. Now, this is an interesting theorem because it says if, and the real mathy words of it, let me look at that real quick. Let a and b be real numbers, so a is less than b, and if f is a function, so the f of a is not the same as f of b, then in the interval from a to b, f takes on every value between a and b. And you're like, wow, Mr. Brock, that's some pretty mathy language. Yes, it is. But let's talk about what that means. It means if a is less than b, which means they're not the same. They're not the same number. So this is really representing the x values. So in this case, let's say a is -5 and b is -1. Okay, -5 is smaller than -1. So a is equal to right here and b is right here. And it says if this is true and they're not the same, they're not both -5, then there exists between f of a and f of b. Okay, how exactly to phrase that? The interval takes on every value. It says between f of a and f of b, every value exists in a polynomial function. So if we took -5 and substituted it into our function, and let's say it equals -4, 1, 2, 3, 4. That is a point on our graph. Because when we substitute -5 into our function, we got -4. And then we substitute -1 into our function, and it equals -2. What the intermediate value theorem says is that every point, every space in between these two, the function exists. Maybe it exists like this. But it's still saying that every value between a and b exists. There's a -4.8. There's a -3 over here. There's a -1.2. There's a -2.8. It's saying in a polynomial function, because in a polynomial function, remember, there's no gaps. There's no gaps. This function may continue on and do this, and maybe this turns around and goes up here, but it's talking about in the interval from a to b. See, if we just look at that interval, guaranteed that if a exists and b exists, it exists in every x between there. You're like, okay, well, that kind of is kind of like, yeah, of course it does. But mathematically, that has to be defined. Everything we do in math, since you've been in elementary school, there is some really fancy college definition like this. Even adding two numbers together, 4 plus 7. There's some real fancy mathematical definition written like this on why 4 plus 7 works. So interesting. Intermediate value. The other thing, extreme value. Okay, extreme value. It says if, same type of thing, f of x is continuous on a closed interval, right? If it exists in a closed interval, then there exists, and we're closing the interval to just between here and there. It says guaranteed there's a maximum and a minimum. Yeah, for this, it looks like the maximum's right here and the minimum is right here. It says it guaranteed. If you have an interval where the graph exists, there has to be a maximum and a minimum value somewhere in that graph. Maybe we're looking at this interval up here and it exists and it goes like this between that interval. Yeah, there's a maximum right there and the minimum right here. This is just a little higher on that side. That's all it's saying. The other thing it says is if this is f of b and this is f of a over here, when we put those in there, if this is a negative value, because it is, it's -2 is what the value is there. Up here, it's a +2. Then it has to have a 0. There's no way you can get from this to that point without crossing the x-axis somewhere. Even if it does this, at some point it has to cross the x-axis. That's what it's saying. So that's the theorems that we get into. Extreme values, minimum and maximums. Minimum maximum values exist. So we looked at a lot of really deep math involving these polynomial functions. Let's look at the assignment. What are they going to ask us about all this? That's what we want to know. First off, just find the zeros, and it's a quadratic equation. Well, that's pretty nice. We can use factoring. We can use the quadratic equation. We can graph it, whatever. Find the zeros. Then it gives us a third degree function. Wants us to find the zeros of that. Again, you can factor it, and you can factor an x out and make it a quadratic equation because there's an x in every term. Graph it, whatever you want to do. Find the zeros and state the multiplicity. Remember, we talked about, I called it duplicity. Duplicity is just 2. Multiplicity, how many of these zeros are there? X plus 7 means there's a 0 at -7, but how many zeros at -7? This means there's a 0 at 7, but how many zeros are there at 7? Find a cubic function. Oh, we'll look at that real quick. I'll show you this before we wander off. And expand the following. Oh, here you go. 2x plus 4 to the third power. Use the binomial theorem or the Pascal's triangle to expand that. Going through the triangle like we did to get the coefficients, multiplying the plus 4 to the third degree, plus 4 squared, all that stuff. Let's look at this real quick because we really hadn't talked about anything like that with a polynomial. Let's say the zeros are 2 and negative square root of 2. All right. I'm not going to do this whole problem for you, but I'm going to show you how it sets up. It says this is the zeros. What is the equation? You're like, ooh, that looks kind of tricky. Well, no, because the thing we talked about where we said that these are all equivalent statement, that x equals a is a solution, x equals a is a 0, so x minus a is a factor. Remember, we talked about all those equivalent statements. Well, that means if this is a 0, then x minus the square root of 2 is a factor. And negative square root of 2 means that x plus the square root of 2 is a factor. And if it's -2, that means x plus 2 is a factor. So now I just multiply those together and I'll get the equation. But you're like, Mr. Brock, have you looked at the answers? There's no square roots of 2 in the answer. Well, if you do the math, x times x, x squared, x times square root of 2 is the square root of 2x. Okay, so that's distributed. Now it's distributed to -2. Negative square root of 2 times x is negative square root of 2x. And square root of 2 times the square root of 2 is 2. This one's negative, that one's positive, so it's -2. And we still have to multiply it by that. What happens when you simplify that? Plus square root of 2x minus square root of 2x cancel each other out. We just got x squared to 2. Our answer is not going to have a square root of 2 in it because they cancel each other out. But that's what you have to do, set that up and multiply them together to figure out what the equation is in standard form. It'll be one of those 4. I threw a lot at you today. When we get into the binomial theorem, that's just a lot to digest. But I did want you to see that before you got out of here because that's an interesting part of math, and you'll get into a lot of. If you're going on to college, you'll see a lot of crazy stuff like that. But it works. That's why it's there, the binomial theorem. It does get the same numbers as the Pascal's triangle, and it ends up with the exact correct answer. It's just a different way of doing things, and it's a little deeper thinking. Wow, that works. And I wanted you to see factorials. If you haven't seen those before in high school, you need to see factorials. It's different, but it's on the calculator, and everyone's like, "What's this exclamation mark?" And memes. You'll see the memes. All right, guys, that's plenty. My mind is swirling. Yours probably is too. So have a great week. It's an A-Day Friday, so I'll be here Thursday if you need to be here or have questions or want to be here. I don't think anyone's below 70% in this class, but if you are, I'll see you Thursday or see you next week. Have a great week, everybody.